everyone. Welcome to EXIMIOUS-EPHOR Joint Symposium, organized as part of the IOHA 2021 conference. I am Dr. Manosij Ghosh from Leuven, Belgium, and it gives me an immense pleasure to introduce you to the moderators of this symposium. First moderator is Professor Peter Hoet. Professor Peter Hoet is the coordinator of the EXIMIOUS project, which focuses on mapping exposure-associated changes in the immunome. This project is part of the larger European Human Exposome Network. Our second moderator for this symposium session is Dr. Anjoeka Pronk. She's the coordinator of the EPHOR project, which is also focusing on understanding of the exposome and health effects in the occupational context. This project is also part of the European Human Exposome Network. First, I give the floor to Professor Peter Hoet to introduce you to the idea of this symposium. And then Dr. Anjoeka Pronk will take you to the speakers and conduct the rest of the symposium. Thank you for joining us again. I give the floor to Professor Peter Hoet.
Welcome at the IOHA 2021 Symposium on Exposure Assessment in the Exposome Context. I'm Peter Hoet from the KU Leuven in Leuven, Belgium, and I'm PI of the EU-funded Horizon 2020 project EXIMIOUS under number 874707. Together with Anjoeka Pronk, she is the PI of another EU-funded human exposome project named EPHOR. We have organized this symposium on exposure assessment in the exposome context. In our human exposome projects, we try to understand better the impact of the environmental factors on health, and we try to shift from one exposure, one disease, to a more holistic exposome approach. Currently, there are 9 EU projects in the European Human Exposome Network, in brief EHEN. 2 of these projects are focused on the occupational exposome, EXIMIOUS and EPHOR. Both projects are involved in implementing and developing of exposome research tools and new exposure assessment methods for both the external and the internal exposome, including sensors, new biomarkers and omics techniques. These tools will enable better joint characterization of the multiple exposures, such as volatile organic substances, minerals, particles, and metals, that together make up our external exposome, and this will improve our understanding of the causes of many environmental and/or occupational diseases. Ultimately, this will improve disease prevention. Through this symposium, we will present the EXIMIOUS and EPHOR experience of developing and applying exposome tools, such as dermal patches, sensors, and new imaging techniques for exposure assessment in the exposome context. By sharing our experience with the International Occupational Hygiene Association, we aim to increase awareness of these ongoing activities in exposome research in the occupational health community. We also hope to stimulate discussion on how these methods and/or techniques can contribute to occupational health practices. I thank you for joining, and I'm sure you will enjoy this short symposium.
The first speaker is Miranda Loh from the Institute of Occupational Medicine in Scotland. She has a background in exposure assessment and epidemiology, and she's worked on applying smart technology for exposure assessment in several EU and non-EU projects. And she will talk about the application of a low-cost sensor box in the EU EPHOR project. Miranda, please go ahead.
All right, thank you, Anjoeka. I'll talk about the low-cost sensor box that we've developed in the EPHOR project. So the EPHOR project is looking at studying the working life exposures and health effects through using an exposome framework. So this means we would like to move beyond looking at just a single occupational exposure and a single disease outcome related to the exposure to looking at integrating different exposures that people might experience during their working life to understand the resultant health effects. And this is important because occupational disease is responsible for about 5 to 7% of mortality in EU countries, and this can cost as much as 2 to 6% of GDP. Now, to do this, we obviously need to be able to measure many different exposures rather than just relying on measuring one at a time. So we have developed a sensor system as part of a larger external exposome measurement system in the EPHOR project. This system includes a set of wearable sensors, as well as passive sampling methods for chemical and biological exposures, as well as a questionnaire that can be done on a mobile phone. So you can see this is really focused at getting more information about an individual's exposure over time. I will focus primarily on the sensor system today out of this modular system. The sensor system will then be used in 2 case studies, which will perform intensive week-long monitoring of their participants. And this will be shift workers as well as general population members, but with a focus on looking at the respiratory health. So the sensor system that we developed includes a sensor box, which measures several environmental variables such as UV, light intensity, dust or particulate matter, noise, temperature, humidity, sleep, physical activity, and heart rate. Physical activity and heart rate are measured using 2 separate sensors, as you can see here. The physical activity sensor is wrist worn and the heart rate is worn around the chest. These can be worn together, and there's a gateway, which is the black box you see in the figure here. The white box is the environmental sensor, and the 2 can be paired, and the idea is that every day the participant should pair the 2 devices, and the data from the environmental sensor will be downloaded into the gateway. This can be done offline, therefore it doesn't need to be connected to the internet, and the researcher can download all the data at the end of the monitoring period. The sensor itself, along with the heart rate monitor, can carry data for about a day, and therefore that is why it needs to be paired every day with the gateway. It is also possible to give internet access to the gateway, in which case the data that's being collected can be viewed in real time. You can see here in the figure the sensor is fairly small and lightweight, and it can be worn on the body either with a harness or on a belt. Now, since this is looking at using low-cost sensors, we want to test this with other monitoring equipment that we have used before. The low-cost sensors obviously allow us to monitor many more things without a prohibitive cost. However, we want to ensure that the data is comparable to other research instruments or the type of equipment that might be used in the field to assess occupational exposures. So we have done 2 sets of testing. One is to use reference monitors in a static monitoring session, and this means we place it in a location which is more controlled, so we can control the exposures. For example, the sound measurements were done in a special room that's used for assessing noise levels. Same with some of the other instruments. You can also therefore use a fairly high-end reference monitor if you're using the doing the static testing. We also wanted to see how this would compare with mobile monitoring equipment that is standardly used in research studies or in occupational hygiene assessments. So we did another round of tests when the person was wearing the sensors as well as these mobile monitoring equipment. So I'll share what some of the results that we've had in this initial testing. First, we did the fixed testing, and you can see for UV and light that basically the sensor compared to the reference, the sensor is on the x-axis and the reference monitors would be on the y-axis. There is, although it's not a one-to-one relationship, there is a clear relationship. It's a linear relationship and it can be corrected for. Therefore, we can develop a calibration equation from this exercise. For the light measurements, the performance at both the low levels and high levels were pretty consistent as well. So low levels would indicate indoor environments and high levels would be outdoors. Similarly, you see a similar type of performance for humidity and temperature where you have a fairly consistent relationship and it is systematically biased, therefore it is easy to correct for. And the same for noise. Now for particulate matter, it's a bit more complicated. We tested it in 3 different settings with 3 different types of primary aerosol, such as cooking, outdoors, and with a fireplace. And they all perform slightly differently in comparison with the reference monitor. Therefore, it's likely that we will have to do calibrations during the field studies in the environments that we know that people will spend most of their time in. This is not unusual, however, for particulate matter sensors using optical particle counters, which is what this particular sensor uses. These types of optical methods often will need to be calibrated to different settings because of the nature of the aerosol when converting it from particle number to mass concentration. The picture becomes more complicated when we compare this to personal sampling equipment. So I show some of the results here, and you can see for noise, we have 2 different noise measurements because our instruments measure both lower level noise as well as higher levels. So the personal dosimeters only really record at the higher levels, and that's the figure on the right. There's a lot of variability, and it's not unexpected. We know that when you compare personal measurements, as in when somebody is wearing a personal sampler and doing their activities compared to stationary sampler, there's a lot more variability due to the movement and the micro scale variations in environmental levels. Some of the variation you see here is going to be due to differences between the instruments, but also to the fact that because a person has to either carry two samplers or wear 2, they won't be in exactly the same position. And similarly, you see better relationships for temperature and humidity, but still it is less clear than in stationary monitoring. The different colors indicate the different environments that the personal sensor has gone through. So this would be something that people may have at home, but also at the workplace. And so we do find at slightly higher levels for some of the environmental variables, there is a slightly better performance. So you have seen now that we've developed a sensor system that can collect high resolution data over time. So the resolution of the measurements are on the level of about every minute. And so that generates quite a lot of data for a week-long period. However, we want to understand more about where these occur and what the participant might be doing. So we have a phone app which asks them every day. It provides alerts so that we can record data about when they go to work, when they're at home, when they're commuting, and then we can therefore match this with the times at which different exposures occur when we do our data analysis. And finally, the hope is that this experience and the lessons that we learn will provide advice that we can put into the toolbox that will be generated from the EPHOR project. The toolbox is aimed at informing scientists, policymakers, and occupational health practitioners. So some of our experiences with using the sensor system and our protocols will be made available for scientists. Certainly the results of the projects will be of use to policymakers, and we are also hoping to create tools for occupational health practitioners to use, based on our experiences, for example, with the sensors. We have already done a stakeholder survey of occupational health and safety professionals to ask them what their experience with using sensors in the workplace might be and how acceptable they think it would be. We've also asked them what kind of information they would be interested in from sensors, as we believe this will become more and more prevalent in the future. We will therefore take some of the lessons that we learned from using these sensors in our studies to help provide advice for practitioners in the future. And that's all I have. I'm happy to take any questions. And here's our project team. This was funded through the European Union.
So the next speaker is Maaike le Feber. She works for TNO. She has a background in exposure assessment and risk assessment, and she works on coordinating multidisciplinary projects in which sensor development is combined with also application research. So research on interpretation of data, for instance. And today she will talk about the development of a sensor that analyzes particle composition as well. Maaike, please go ahead.
Thank you, Anjoeka, for the introduction. The title of my presentation today is Beyond Particle Detection, and I'll explain a bit why and how we did this, how good it is. I'll give an example, and I will tell a little bit about future work. So today, many particle counters are available, differing in quality, in accuracy, and also in price. And they all measure number counts of particles, size distribution, or mass concentration. And as you probably know, a metric discussion is still going on. What is the best metric to express particle exposure in? And it is because different characteristics are determining the particle toxicity. So besides size distribution, also chemical composition, solubility, reactivity, shape, and surface area play a role in particle toxicity. We decided to first focus on the chemical composition. So we developed a device that you can place in parallel with a particle counter that can identify the composition of the particles. It consists of a cyclone to concentrate the particles that is connected to a hollow waveguide. A hollow waveguide is there to synchronize the PM flows and the light of a spectrometer. And the spectrometer will produce the spectra of the composition of the particles. So what does it look like? Here you see our portable CID, as we called it. It's about the size of a small shoebox, and it consists of three compartments. The first compartment contains the electronics. The second compartment contains the pump, and the third contains the sensing elements. So the cyclone to concentrate the particles, the waveguide to synchronize the particle flow with the light, and some connectors to make it all happen. So how does it work? In principle, our CID measures a full infrared spectrum, but we decided to first focus on the construction dust and crystalline silica in particular. So I'll try to explain how it works in a very simplified example. Construction dust contains four typical components. So it's crystalline silica, amorphous silica, calcium carbonate, and calcium sulfate. Each of them are characterized by a specific absorption peak at a specific wavelength. So if we have the combination of all particles in the hollow waveguide, we get a spectrum with four typical peaks. So the wavelength of each of the peak identifies the compound, while the height of the peak in relation to the other heights can be used to calculate the fraction of each of the substances in the mixture. Of course, this is a very simplified example. In reality, it is a bit more complicated. So here you see the 4 spectra of the same substances, and I would like you to look at the upper 2. So on the left, it's crystalline silica, and on the right, the yellow one is amorphous silica. What you can see at the arrows is a steep decline in the amorphous silica from the peak back to almost 0. While for crystalline silica, this slope is less steep than for amorphous silica. So that is quite a difference between crystalline silica and amorphous silica. And to verify whether we can distinguish between the two, we took the spectra of 2 mixtures. Mixture 1 contains equal crystalline silica and amorphous silica, while mixture 2 contains mainly crystalline silica. And as you can see, again, at the arrow, the slope of the gray spectrum is less steep than the red one. So yes, it is possible, even though it's not a very specific peak for the different substances, to distinguish between the substances from the spectra. So we developed a calibration matrix. So in fact, what it does, we developed an algorithm that fits the spectrum of an unknown mixture to the known spectra. And by that, it can calculate the fraction of each of the 4 components. Of course, we've tested our system in an experimental setup. Here you see a setup that was used outside our laboratories. So it was done outdoors. And what you see here is a Dermal. It's a grinder which produces the dust. And since there's no golden standard, we use a filter sampling. So the inlet of the filter is signaled in the picture. We also used TSI as a high-end particle counter. We used our own CID in parallel with an AlphaSense particle counter. And we used this experimental setup on 5 different materials, differing in the amount of crystalline silica that was in the material. So the percentages here refer to the content of crystalline silica. So the filters were taken and were analyzed after the experiment using a variation on the ISO standard for workplace air assessment. By that, we could define the crystalline silica content on the filters, and that could be compared to the CID measurements. So in the pictures on the right, you see that the crystalline silica measurement was far from constant. This has partly to do with non-homogeneity of the stones, and partly with the fact that we did the experiments outdoors and it was a windy day. So in the table below, you can see the different crystalline silica content of the materials as established by the different methods. So sandstone with the CID as well as with the filter measurement has obviously more crystalline silica than cellular concrete and then gypsum, which is in good parallel with what literature reports on the crystalline silica content of these materials. As you also can see, is that the CID measurements are not identical to the filter measurements. That is something that we didn't expect because 2 different methods are used. So the CID makes use of a transmission method, while the filter was assessed using ATR, which is a service technique. Both FTIR are methods. So after the experiment at our own facilities, we took the devices to a construction site to see how the device performed in real life. We measured different activities and on different materials, And also here you can see that the measurements of the CID and the measurements from the filter sampling are pretty much in line, even though there is an average difference of about 10%. We expect that we can reduce this difference by better data processing and further calibration of the spectra. So for the ones interested, we also provided real-time feedback through an app when we were at the construction site. I won't go into detail, but the sensor data were captured, stored, and transformed into information by a data platform EXIMIOUS, and this is what the feedback looked like. So some future work. Of course, we need to further calibrate the device, and after that, we will perform a proper field validation study. That is something that's absolutely necessary. But in parallel, we started to miniaturize the CID, miniaturization into a wearable sensor. This wearable sensor will likely be specific for one component at a time, and it will be integrated with a particle sensor. So you get one device instead of two as it is now. Our first target will be crystalline silica. But as you may understand now, the CID is also capable of measuring other substances than crystalline silica. So that was it. Thank you very much for your attention.
Okay, so the next speaker is Murali Jayapala. He works at imec and he has a background in computer science. And today he will be talking about the application of spectral imaging for exposure assessment and its possibilities in the EXIMIOUS project. Please, Murali, go ahead.
Thanks for that introduction. I'm a researcher in a research institute called imec, and we are part of the project in the EXIMIOUS, and where our role is to try to see if we can bring some of the novel technologies of hyperspectral imaging into this exposure assessment context. So just to start off briefly, what is hyperspectral imaging? I think probably many people in the field would know a lot about spectroscopic techniques, where the idea is that you have a broad light source and then you look at the reflectance of that and you measure the reflectance spectra. And on the other hand, we also know, conventional imaging. Yeah, we all have mobile phones, we all take pictures, and we are able to take images and look at the color pictures. Hyperspectral imaging is sort of the combination of the two. On one hand, you have the spectroscopy, where you have a point location and you get a lot of information, and there are spectra. And the imaging, where you have limited spectral information, but you have a lot of spatial information. The combination of the two together is typically where we end up as hyperspectral imaging, where you have a lot of spatial information. I think that is one of the key aspects, having spatial information. And at each location in that space, then you also have the spectral information, unlike typical spectroscopy. Now, of course, like I mentioned, spectroscopic methods, there are plenty of other techniques. The general principle is always you have a light source and it interacts with the matter and it gets either absorbed, reflected, or scattered. And you can do this kind of principle in different wavelength ranges, whether it's in visible light range or in near infrared or short infrared and so on and so forth. Depending on the type of material you're looking at, different wavelength ranges might become relevant. I'll come back to that a little bit later. And in terms of techniques, there are quite a few techniques as well. I briefly mentioned the point-based spectroscopy, but there is also other kind of spectroscopy like, Raman spectroscopy or even the inductively coupled plasma spectroscopy. Some of them are a bit more destructive techniques. Some of them are non-destructive techniques. But given all these different plethora of spectroscopic techniques, sometimes it's difficult to distinguish one from the other. Now, specifically what we are talking about is more on the reflectance spectroscopy. That's where the technology that we want to talk about today. and specifically on imaging. So combination of imaging and spectroscopy. And the reason we want to talk about this today a little bit is also some of the new opportunities that is coming up, in especially in miniaturized systems, and that enables bringing this kind of imaging systems into the field and into the places where it becomes relevant. So this where does this hyperspectral imaging comes from? I think it has a lot of applications, especially in the space and remote sensing. I think 50, 60 years ago, it has since then, or even longer, perhaps, hyperspectral have been used in a lot of remote sensing application. There's just a couple of recent examples, I would say. Even in the International Space Station, there are a couple of instruments which is capturing hyperspectral images, both in visible, near infrared, and short infrared ranges. Even more recently, the Mars rover, which is roaming around on the surface of Mars, also has a couple of multispectral or hyperspectral cameras. And these cameras are used for various purposes, and I think in this case they use a little bit for navigation, but you could also use for analyzing some of the properties of the samples that you're exploring. But of course, all these systems are fairly large and bulky systems, and that's where the more recent progress in the last few years is interesting and brings up some of the new opportunities. And one specific way, or the one specific technology development that is happening is in our research group here in imec, where what we are trying to do is we are trying to look at how we can miniaturize these systems. So here is an example of a big instrument for a visible to near infrared range system. And typically the architecture of that is you have a lot of discrete optical elements inside, and one of them being the key optical element, which is the diffraction grating, which is splitting the light into different wavelengths, and then that gets collected into a certain specific sensor. Now, what we do at imec is we try to minimize as much as possible all the discrete components and the bulky components, and try to integrate the light splitting aspect or the filtering aspect directly into a detector device. And this we do it in different ways. And imec being one of the research center here, looking at semiconductor technologies, we want to use the technologies of typical semiconductor or chip manufacturing techniques of deposition, patterning, and wafer level processing, and so on, to see how we can mass manufacture these sensors. Just to illustrate a little bit, the filters that I talked about, we can deposit them directly on what we call as image sensor wafer devices. This is like a 20 millimeter image sensor wafer, which typically houses hundreds of sensors to thousands of sensors, and we can deposit and pattern these kind of filters at pixel level, with very high accuracy at micron or even submicron level, and we can pattern them in different ways, line scan, snapshot, or even per pixel level. Now, once you do this kind of deposition, the advantage then is your whole spectral sensing device becomes this small chip, and then the electronics around that can be miniaturized. So we have different flavors of these cameras that we are working on, and more recently we also have very smaller camera. And then you see for this kind of a camera and imaging system, even the lens itself is slightly bigger, but of course we can find miniaturized lenses as well. And then also you can even miniaturize it much more further to a small device. And this device is actually more like a spectroscopic device, but there is no reason why we could not do that for an imaging device as well. And this kind of sensor can easily fit into a portable device or even our mobile phones. So this enables, or this is some of the recent work that has happened in the last few years, as imec is one of the contributions in that, but there are other companies in the market these days trying to look at similar technologies. Miniaturized systems yeah, it's enabling a lot of new opportunities in this space. So an example here, what I show here is a video of how our technology can be used in real-time detection and identification of objects. An example here is you see here things like all blue objects. It's typically very hard to distinguish, but in real time, we have the camera here, and with standard illumination, we are able to distinguish the different types of the objects which are there based on the fact that each of those samples will have different reflectance spectrum. And these are another example. Each sample will have different spectrum, although they might look visually to be a similar color, but from a reflectance point of view, from the spectrum point of view, they all have different spectral signatures, and you can use that to distinguish and identify these materials. And that's one of the unique things about hyperspectral imaging. Yeah, here we can do not only for a single point, we can do it for a whole area. Yeah, and that's the key part: imaging and spectroscopy, and that's the novel thing. So imagine this kind of a miniature system that you take into the field and or putting into the mobile phone creates a lot of new opportunities. So why we get so excited now also is that yeah, this technology is gaining traction in a lot of conventional imaging applications or remote sensing applications. Yeah, like in using these kind of sensors on an agriculture field, in more remote sensing or agriculture. Also in sorting of different materials, so different types, food sorting, waste sorting, and all those kind of things. But also in medical devices, especially in surgery, during surgery, to do different type of tissue identification, tumor, non-tumor application, distinction, but also in a lot of cases in gas leaks and camouflage and security and so on. So this is some recent work and recent application pull that we see and interest, and largely coming from more conventional vision applications where regular cameras were used. But now imagine using this kind of spectral cameras will enable a lot of rich information and a rich way to identify and distinguish materials and things. So that brings us to a little bit, yeah, what's our interest in EXIMIOUS and how we are trying to leverage this technology there. And the project of EXIMIOUS is basically trying to assess the link between the exposure-induced particles and how this affects the immune diseases. There are different exposure samples that are being considered. Yeah, crystalline silica, other types of silica on the skin and breathing locations, volatiles, organic substances, particulate matters, some organic materials, including microplastics and some polymers, but also some other indoor specific components and so on. Of course, for all these materials, there are established standard current techniques. There are existing state-of-the-art techniques. Many of them are also ISO certified, and that typically always have as a basis some kind of sampling. You collect the samples from the environment, either on filters or in some tubes or whatever that might be, and that sample get analyzed in big instruments today using gas chromatographs or mass spectrometers, or even these X-ray diffraction analysis, which are all like huge tabletop instruments. So what we see is that, and why we are also still excited about hyperspectral is at least some of the bulk materials we have seen with our cameras and also in some literature that they have some unique signature, spectral signatures, especially for plastics. You see, yeah, there are unique spectral signatures. Even for textile materials with different bulk materials at level, you see a lot of different spectral signatures, and we can easily identify them. Some of the particular matter also, like silica here in this case, they also have some good spectral signature. So this gives us an interesting opportunity to see, okay, why not do imaging and do spectroscopic analysis and do some direct reading. That's basically what we are trying to do in a nutshell. We are in the early stage today and trying to see how we can explore this technology. And the idea would be that we make a miniature device, put it into either a mobile phone-like system or a portable system with some analysis behind that. And then you could point this kind of device directly into an work environment, either onto a desk or to a skin of the people, or on the clothes, and then sort of give a direct reading. Perhaps not the direct reading as a lab instrument would give, but at least a qualitative assessment, saying that that there is a certain abundance of certain material like silica or something else, making a qualitative assessment that we think could be potentially feasible. So to do that kind of to go towards that target, we have some planned activities. Right now, we are still trying to see, collect with some current sampling methods, and then trying to see how we can distinguish these different spectral signatures on the sample substrates with imaging techniques, spectral imaging techniques, and of course compare that with the traditional methods and do the correlation work. I think for now, most likely using the spectral imaging techniques, we will probably focus on metalloids and crystalline silica, and maybe some organic dust and carbon. And that could be our focus. But of course, we still have to figure out the key challenge, like some of the properties of the spectral signatures at the bulk material level, and the particles and aerosols are slightly different. So we need to also look at how the imaging aspect and the spectroscopic aspects work together and come up with some good solution. So that's in a nutshell, where we are today and what the plans are. We hope this spectroscopic imaging technique could be a very valuable tool that could enable us to do exposure assessment in the field. So thank you. Hopefully, if you have any questions, I'll be happy to answer them.
Okay, so we're now at the last presentation of this session. The last speaker is Jeroen Vanoirbeek. He has a background in biology and toxicology, and he leads the Laboratory of Occupational and Environmental Hygiene at the Catholic University of Leuven. He will talk about the relative contribution of both dermal and inhalation exposure to the internal dose today. Please, Jeroen, go ahead.
Thank you very much for your kind introduction. I will take my pointer here. So I will be presenting mainly on dermal exposure versus inhalation exposure, and see what the relative contribution is, as already mentioned. So we know that we have a lot of exposures on the workplace, and there's been a lot of focus in the last 40 years on inhalation exposure, and we know which health effects it has, and we can measure it quite good, and we can model it quite good, and we know what to do. But on the other hand, an important other exposure on the workplace is dermal exposure. And this is less known, this is less easy to model, but it has an enormous contribution to health effects. There are a lot of health effects. Some studies even suggest that there are more health effects due to dermal exposure than there are versus inhalation exposure. And if you look at which type of exposure, you have all kinds of exposures, and this is a little bit the incidence rate of skin diseases in different settings. And you see mining and quarrying is a big one here. Construction has a lot of health issues due to dermal exposure. Now, if you then want to go and see what is dermal exposure, or at least how much dermal exposure do we have, then you need, of course, a good method to quantify it. And here we start with a very analog method, ACC patches, to quantify dermal or to try to quantify dermal exposure at least. And then I will show you some data on the real application in an occupational setting of this. So let me start with dermal sampling. You can do that via in situ techniques, you can do that via removal techniques, or you can do that via interception techniques. And this interception technique, that's the one that we have selected. And I'm showing that here in a little bit more detail. So you have your activated charcoal clot patch here. With an indicator strip which changes color when you have exposure, but it's absolutely not sensitive. And we rather go for the analysis of the activated charcoal. And why did we select this one? Well, here you see the skin surface. You have an actual site of exposure, that's the red part, and you have a droplet on top of it. Yeah? And you see here, you have a deposited mass of a certain compound. Partly it's absorbed, yeah? It's the absorbed mass, and then you have part is also desorbed. So if you take the removal techniques like a skin wipe, then you take at one certain moment what is deposited on the skin. If you use tape stripping, then you will have at that certain moment, you will have the deposited mass and perhaps a little bit of your absorbed mass, which is in the very top layers of the skin that you take with the tape. But if you have this patch, yeah, which all has the absorbed, the deposited, but also the desorbed mass, because it sticks to the activated charcoal clot. So it might be a little bit overestimation, but we'll see later on how we deal with that. So you have here the charcoal patch, you can remove it. And we have developed a method to identify and quantify 181 VOCs at the same time. We had to define desorption efficiencies for both the apolar and the polar components, and some of them even need a Dublin curve. We had done storage experiments, both at room temperature, but also -4, -20, and -80 degrees, which preferably we want to store them for a low temperature. And in the end, we came out that they in fact have a good capability to get the VOCs off and to estimate possible exposure. This has been published a few years ago in the Annals of Work Exposure and Health. More interesting is, of course, the application of these patches, yeah? And how then to estimate thermal exposure and how to correlate that or to relate that to inhalation exposure. And for this, we had a field study in a small cohort study with 37 participants in a thermoplastic panel factory. And we had 4 different exposure groups. We had the sheet molding composite workers. And in fact, what they did was mixing a lot of chemicals together, yeah, but not really having direct contact with that. Then you had the hydraulic press workers, that's this green machine here. And these workers actually grab hold of the thermoplastic panels and got contact with them. Then you have mechanics walking around through the factory, making sure that all the machines worked. And you had office workers with an open door connected to the workplace. We measured thermal exposure with our validated ACC patch. We also applied risk of therm to estimate the thermal exposure. Inhalation exposure was measured in a passive way with organic vapor monitors. And then we did also biomonitoring via urine collection. So this is how we applied everything. Here we have in the breathing zone, the 3M monitor. We have patches on the hand, one on the thumb, one on the index finger. And this is for estimating or measuring real contact, while we have one extra patch in the neck, and this is to see what the vapor contribution to skin contact in fact is. We had a few exposures, not much. It was quite selective, and let's start with acetone. What you see here is dermal exposure expressed in micrograms per square centimeter. You have the HP workers, then you have the SMC workers, you have the mechanics and office workers. The first one is the thumb, the second one is index finger, and the third is the patch in the neck. And what you see is mainly the sheet molding composite workers mixing the chemicals, working a lot with acetone, and they have quite some acetone on the dermal patches. And it is the same for the 2 patches on the hand as it is for the neck. So that indicates that it's mainly vapor exposure. Also, these workers have high inhalation exposure. You see here the TLV, 594 milligrams per cube meter, while the other ones, the other 3 groups, have almost no exposure. And this was also shown in biomonitoring. So acetone directly measured in urine. This is the biological exposure indices. The average and the standard deviation are just below the bay. So then we have styrene. Styrene was abundantly used to make these thermoplastic panels. And what you see here, it's the HP workers, the hydraulic press workers, who actually touch these panels. They have very high values on the thumb and on the index finger, and a lot lower on the neck. So this is in fact the contribution of the vapor. And these 2 high values are contributions of direct contact with the thermoplastic panels. While the sheet molding composite workers, they had to mix and bring the styrene, but they didn't have direct contact. And you see the 3 concentrations are the same, and the same as the HP workers. So it's kind of an aerosol contact and not a direct contact. Also, we could detect them with the mechanics and not in the office workers. Risk of derm gave us, for these 2 tasks, gave us these estimates. So approximately good for HP workers and slight underestimation for sheet molding composite workers. And that depended on the proceedings that we had or only could choose in risk of derm. If we measured the inhalation exposure with the OVM passive monitor, you see that this was the same for both the HP workers and the sheet molding composite workers, and they went way above TLV, so exposure was really too high at that workplace. And if we then go to biomonitoring, we were expecting that we could see this part of dermal exposure in the biomonitoring of the HP workers. And here we had phenylglyoxylic acid along with mandelic acid, which are 2 markers for styrene exposure. But in fact, we had no statistical difference. You see a slight difference, but it's not statistical between the HP workers and the sheet molding composite workers. So from this biomonitoring, we could not determine the relative contribution of this actual skin contact here. So we went 1 step further, and what did we do? Well, using the patches on the hand, we were estimating, in fact, liquid contact, as said, and the patch in the neck was for vapor contact. Then we went to see what, in fact, the surface size is of the hands and the forearms, and estimated that at 2,000 square centimeters, neck and face at 1,100 square centimeters. And this allowed us via IH skin perm to estimate or to calculate how much is actually absorbed of the amount of styrene that we found on the patch. So you see here the HP workers, they had a lot more styrene on the patch versus the SMC workers. These are the absolute numbers, and these are retrieved from the patches on the hand, index finger and thumb. But we also know that not everything that comes into contact with the skin is absorbed. So in fact, if we go via IH skin perm, we know that only 6.5% of this 1,700 is absorbed versus 22% of this 410. So in fact, what we see is that the actual amount absorbed via the skin is kind of similar between these 2 groups, and the vapor is very low compared to the actual contact to liquid contact. So for acetone, which is much more volatile, we have here exposures that are way lower, 2 milligrams per hour and 414. And you see that the amounts absorbed here are significantly different, thereby also saying that here you have a contribution to dermal uptake. Now, if we can calculate the uptake for the skin, we can also do this for inhalation exposure. And there you have this formula to estimate how much you have absorbed via the lungs and comes into the body. So D is uptake of inhalation exposure, and you can calculate it via the concentration in the air, which we measure with the 3M monitor. You have the intake rate, the exposure factor, which is unitless, and it takes into account body weight. And we did this for styrene. These are the values, quite similar what we found in the air of that workplace. We know the intake rate for styrene is 66%. And then you see here that the absorbed amount is approximately the same between these two workers. For acetone, we had very high exposure for the SMC workers and much lower exposure to the HP workers, and this reflects also in the dose that is actually absorbed, of the amount that is actually absorbed. You see, acetone is more volatile and it has a higher intake rate than styrene. Now, if we compare these absolute amounts of inhalation and dermal exposure, well, then we see here that both for inhalation exposure, but also for dermal exposure, it's similar to the two working places, HP versus SMC. But what was much more striking, that the values were in the same range. So we actually had here a relative contribution of 50-50, where intuitively, you estimate that you have the major exposure via inhalation. This is not correct, depending on the component that you have. Here we show that styrene has a 50-50 inhalation. But if you then have a much more volatile compound like acetone, then you see that the relative contribution, it's almost fully via inhalation and only a very, very limited amount via skin contacts. So depending on the component, the relative contribution skin versus inhalation differs a lot. So what can we conclude? In fact, the ACC patch, we could quite good monitor dermal exposure. This was certainly positive, but only doing then biomonitoring, urine biomonitoring, we were not able to differentiate between what actually came in via inhalation or the skin. We needed for that one IH skin perm, which also downsizes a little bit the patches because it does have some overestimation, but with IH skin perm, including that one, then you can really estimate what comes in via the skin. And so main conclusion, depending on the component that you're assessing, you can have up to 50% of your total intake or your internal dose can come via skin exposure. This we recently published in toxicology letters. But still, this is a very analog way of assessing skin exposure. And we also want to move from an analog ACC patch to more innovative sensor. And this is a picture taken from this publication. And in fact, what we want is a sensor in the similar size of this ACC patch. And I'm showing this picture because we know that we need 1, a sensor, 2, an antenna, 3, a battery needs to be included. So that will be similar in this size. This would allow us to have a continuous readout, and this could, for example, identify breakthrough times under personal protective care. We can have a total exposure, or we would like to have at the end of the working day a total exposure. But then again, a lot of development still needs on sensitivity, selectivity, and accuracy. And this means that now we can go in almost in the nanogram range with this ACC patch. We can differentiate 181 different VOCs, but here it will be a lot more difficult. Probably we will go to the major groups of chemical structures, and then how accurate it is, that also will need a lot of experiments and validation. So a lot of people to thank that generated this data and helped with this research. I am part of the EXIMIOUS group. Here you see a picture of, I think, 1/3 or 1/4 of it with the first physical meeting, and I hope to see these people soon again, and a lot more will be there. And thereby I will end my presentation, and you can ask questions if you like.
Thank you very much, Jeroen, for this interesting presentation. And indeed, it's now time for some questions.